Hi, this is Don, K2PMC. You may have heard some hams say that a vertical antenna radiates poorly in all directions. Well, this does apply if the vertical does not have an efficient radial system to work with. But if you team it up with a decent radial system, it's a totally different story. In this video, I'm going to show you a very simple 40-meter vertical that works very well. Then I'm going to compare it against a 40-meter dipole at the same height. So stay tuned. The modeling system I use is EZNEC. EZNEC is pretty much the standard, has become pretty much the standard for antenna modeling. Now I'm going to start out with the 40-meter dipole. Okay. Now here's the 40-meter dipole. And you can see it's 67 feet long and 35 feet high. Now I've done a plot, an SWR plot, just to show you what the SWR curve would look modeled over. I model it over sandy soil because that's where I happen to live right now. Now the first thing we're going to look at is an azimuth plot. Don't be concerned about the elevation angle here. We'll talk about that later. But this is going to give you an idea of the radiation pattern of this 40-meter dipole. The dipole is in this north to south plane. Now here is an elevation plot of that dipole, which is at 35 feet. The green circle here means the maximum radiation. So the maximum radiation takes place at a cursor elevation of 62 degrees. So basically, most of your power is going to be going out at 62 degrees. Now we're going to take a look at the vertical. The vertical, it's a quarter wave, 34 3/4 feet tall, which is why I chose 35 feet for the dipole. I wanted to have the height at the same elevation. There are your two radials. We'll talk about radials later. Now here I did the same SWR plot for that 40-meter vertical, and you can see it's got a pretty good bandwidth on 40 meters. Okay, we've seen how the vertical and the dipole are laid out. Now, if you recall, here's our dipole. Here's an elevation of the dipole. The maximum radiation was at 62 degrees. Now, what I've done with the dipole is I've changed the plot to an azimuth plot, and the elevation angle is 62 degrees. So let's see what that looks like in the azimuth. Now, you'll notice that, first of all, the figure 8 pattern is pretty much gone. What we see now is it looks like a vertical because it's perfectly round. Now the reason for that is as the angle of elevation, in other words the takeoff angle, increases, the antenna, the pattern begins to become more circular. Okay, so at 62 degrees, let's see how that compares to the vertical antenna at 62 degrees. Now, if you look up here in the upper left corner, I brought in a display of the vertical at an azimuth of 62 degrees. That's this red circle here. Now, at 62 degrees, the vertical is 13 dB below or less than the 40-meter dipole. So that's more than 2 S units. So clearly, when you get up to 62 degrees, the vertical is certainly not going to work very well. So the dipole at 35 feet is going to be a very effective antenna for things like net control stations and out to several hundred miles. You're going to have very good coverage in almost all directions. It's only 2 dB down at its worst point, in fact less than 2 dB, which is not even half an S unit. So it's going to be a very good antenna for relatively short range communications on 40 meters. Now, what I've done on the dipole is I've reduced the takeoff angle from 62 down to 40 degrees. Now notice we start to get back closer to the figure 8 pattern. It's more of an ellipse now. And the forward gain, which was about 6 dB at 62 degrees, has dropped almost 1 dB down to 5.2 dB. Now, let's see how the dipole at 40 degrees compares to the vertical at 40 degrees. Now, if you noticed, at 62 degrees, the dipole was almost 13 dB better than the vertical. Now that has dropped from 13 down to 7.5. So that's 1 S unit, 6 decibels that it's dropped. Now, it's still stronger, but notice in the north-south plane, it's only about 1 decibel stronger. Now I've changed the takeoff angle to 30 degrees. Let's see how the dipole compares to the vertical at 30 degrees. I notice things have really started to change now. In a north-south direction, the vertical is 3 dB stronger. That's half an S unit than the dipole. The dipole still prevails in the east-west direction, although it's dropped now from 7.5 to just a little over 5 dB. It's interesting to note that 30 degrees is significant on 40 meters because studies have shown that on 40 meters, half of the time the signals will arrive above 30 degrees, half of the time the signals will arrive below 30 degrees. So 30 degrees is sort of a cutoff point. Now, I've dropped the takeoff angle on the dipole to 20 degrees. Now, if you'll notice, in the north-south direction, the vertical really starts to gain an advantage over the dipole. Significant. In the east-west direction, the margin has decreased to less than 3 dB, which is less than half an S unit. And when I said cutoff point, what I'm really saying is most of the signals that are going to be arriving above 30 degrees are going to be the relatively close-in signals. Most of your DX signals are going to arrive below 30 degrees. So let's see how that works. Now I've dropped the takeoff angle to 15 degrees. Now, if you notice, there's less than 2 dB difference in the east-west plane, and there's really no comparison on the north-south radiation pattern. So you can see as your angle of elevation decreases, the vertical really begins to take advantage of the situation. Now, let's see what happens when I've lowered the elevation angle down to 10 degrees. Now you can see there's really no comparison. The vertical is superior in all directions. So you can see why vertical, if you're looking for low angle radiation, long range communications, the vertical is going to be a better antenna. Now there are guys that are going to say, oh, he's full of baloney. I've worked DX with my antenna. My antenna is only 35 feet off the ground. Now, I didn't say that you're not going to be able to work DX. You certainly will work DX with an antenna only 35 feet, a horizontal antenna only 35 feet off the ground. But where the vertical is going to have an advantage is in the number of hops or skips that are going to be required for your signal to get to that DX station. Whereas with the dipole, it's going to require many more ionosphere to Earth bounces to get out, let's say, 3,000, 4,000, 5,000 miles, many more than it will with the vertical because of that lower takeoff angle. Consequently, the received signal at the other end is going to be stronger. We've looked at the radiation patterns on both antennas. Now let's talk about the vertical antenna, and more specifically, the radial system. Now, I've got the red lines here. Could be confusing. These are the current lines, and these are the axis lines. The y-axis, which is north-south, the x-axis, which is east-west, and of course your z-axis, which is your height. So bear with me for a minute, and I'm going to remove those. Well, this might make it a little easier. So here's your radials. Your radials are full quarter wavelength radials. And that's very important. They're 33 feet long. And the vertical radiator is just about 35 feet long. Now you're looking at an elevation projection of that vertical with 2 radials on the ground, and you can see the gain is minus 3.2 dBi. Now we're going to compare that to the same vertical with 16 radials on the ground and the same vertical with 2 elevated radials. Okay, what I've done now is I've taken our vertical and I've added 14 more radials for a total of 16 radials, each 33 feet long. So you're talking just about 2,000 feet of wire for radials. Now, what you're seeing here on the left is our 2 radials on the ground antenna with a gain of minus 3.2. Here's our 16 radials with a gain of minus 0.14. So you can see when you added the 14 extra radials, you gain 3 dB, which is considerable when you figure it takes twice the power to gain 3 decibels. Now, what I've done in this frame is I took the 2 radials that were on the ground and I just raised them a foot. Notice, by raising them a foot, I reduced the ground losses by 2 decibels. That's significant. Now let's take a look at the radial system with 16 radials on the ground, had a gain of 0.14. Now, if you look at our 2 radials, which are a foot off the ground, it's a gain of minus 1.24. So we are now just about within 1 dB of the 16 radial system. Now in this frame, I've taken the 2 radials and I've raised them to 36 inches off the ground. Now you can see that I've closed the gap to just about 0.6 of a dB between the 16 radial system and this 2 radial system. 0.6 of a dB is something that you just would never notice. So what does that tell me? Well, first of all, it says you don't have to lay down thousands of feet of wire to put up a good vertical antenna. If you can get your radials a foot, 2 feet, 3 feet off the ground, you're going to have a pretty efficient antenna system. Well, the next problem is, well, I live in a small city lot. I don't have room for 66 feet of radials. Can I bend them? Well, the answer is yes, you can. Now here, I just arbitrarily bent these radials. This part is 20 feet. This part is 13 feet. I did the same thing on the other end. They don't have to be exactly 20 and 13. But the thing you must remember is that the radials have to be separated by 180 degrees for your radiation pattern to be symmetrical. If you start changing the angle of the radials with respect to each other, you're going to start changing the radiation pattern of the vertical so that it will no longer be omnidirectional. And as you might imagine, there's a millions of combinations that you can come up with. Okay, well, we've bent our radials. How does that compare to the straight radials? Well, here's our straight radials, 36 inches off the ground. We had a gain of minus 0.78. Here's our bent radials at the same height. And we have, for all intents and purposes, the same gain. So what that means is you can change the geometry of your radials. But as I cautioned before, if you want an omnidirectional pattern, the radials must be as close to 180 degrees separation as possible. Now let's take one last situation. let's say that you really can't have your radials running through your yard. It's just not practical. But you do have a fence surrounding your property. So you say, well, can I put the radials on the fence and have their vertical mounted on the ground? Will that work? Well, the answer to that is yes, it will. Now, what I've done here is taken a vertical. It's mounted at ground level. Here's our radials. And our radials are at 5 feet. And I've run a little connecting wire from the vertical base to the radials. The vertical is mounted a foot away from the fence. Now, I'll say this. The farther you make this connection, the more your loss is going to be. So I wouldn't have the vertical 20 feet away and then the radials mounted on the fence. I don't think that's going to work too well. So let's see what that looks like. Now, in this frame, I'm comparing our 5-foot high radials mounted on the fence back against our original 2 radials on the ground scenario. And you can see we're still 2 decibels better than the ground mounted radials. Now, before I wrap this up, I've got a couple more things to say. First off is I built this vertical. The vertical is made from number 14 wire, all the elements. The big difference is I'm fortunate that I have some tall pine trees, and I was able to get this vertical up to a height of 65 feet. Now, you'll notice that the radials are drooping. The advantage that elevating your vertical, I should say, gives you is that you can adjust the SWR of the antenna by varying the angle of the radials. Now, to show you what raising that vertical does for the efficiency of the antenna, what I've got here is the outside is the vertical at 65 feet. The red trace is the vertical that's at 3 feet. And you can see that's 3 decibels difference between the low vertical and the high vertical. And 3 decibels is significant. The other thing I wanted to mention was with respect to feed lines. When you're feeding an antenna with coaxial feed lines, such as you would be with this vertical, whatever you do, do not use RG58 or one of the smaller coaxes. It's going to cost a little more, but use like an RG213 or LMR 400, because the difference in loss per 100 feet is amazing. Many amateurs don't realize it, but a lot of their signal is lost in using an inferior, I don't want to say inferior, a coaxial feed line that has much more loss per 100 feet than the RG213 or the LMR 400. For short patch cords or things like that, yes, I use it here in the shack. RG58 is is good. You know, your big stuff is very hard to work with. But when you're talking about a reasonably long run of coax, by all means, go for the bigger stuff. So that wraps it up. I hope you liked this video. If so, give me a thumbs up. I'd like to hear your comments, if any. And see you on the bands. This is Don, K2PMC, saying 73s, and we'll see you.